Hi, welcome to this video. Were imaginaries, that is, imaginary numbers, really imagined? Where did they really come from? Many presentations of imaginary and with them complex numbers explain these with a story exposed long since as false. They say that one day mathematicians created a solution for the quadratic equation x squared plus 1 equals 0, equivalent to x squared equal minus 1, has no real solution, so mathematicians, they say, just invented a number to fit the bill. Despite the rule minus times minus is plus, which turns the square of even a negative number into a positive outcome. Oh, please, hold on to your seats. Let's make some space. Dirk-Jan Strijk, professor at MIT, mathematician and mathematics historian, wrote in A Concise History of Mathematics, a book he wrote in 1948. See, for example, the 1954 edition on page 114. It's on the internet. It is a curious fact that the first introduction of the imaginaries occurred not in the theory of quadratic equations, where our present textbooks introduce them. What he called the present textbooks were, of course, the textbooks of 1948. That's a long time ago. Oops. That's a wrong story for you then. So you saw no need here for a new imaginary number? Perfect. Neither did the mathematicians. So much for rubbish. Part 1. The first introduction of the imaginaries occurred in the theory of cubic equations, in the case where it was clear that real solutions exist, though in an unrecognizable form. Cubic equations, where real solutions exist. So nobody invented any solutions at all. A really messed up story then. Well, it hides a big embarrassment. Cubic equations then. Okay, let's see what did happen. Almost 500 years ago, a problem unsolved for thousands of years was finally solved. Nowadays, we write it this way, a cubic equation. For those who forgot about equations, each such equation, of this case, is shaped by the values represented by P and Q, and therefore the unknown number, signified by x, will depend immediately on these P and Q values. So what people had been looking for during thousands of years was a recipe, we say a formula, telling you how to use P and Q to compute the unknown x. And at last, recipes had been found by two people, a university professor, Scipione del Ferro, and a self-taught mathematician, Niccolò Fontana, called Tartaglia. Nowadays, one single formula is enough, because our modern notation presupposes the rules of signs are being used. And this is the formula derived by our fully legal school algebra. X is the sum of two cubic roots, and in each cubic root we have minus q half, followed in one of the cubic roots, here the left one, by a plus, and in the other cubic root followed by a minus, themselves followed by a square root, and in each of these two square roots the same expression. People were excited and quickly tried it out, first to their full satisfaction on many equations they made up, but very quickly too they spotted trouble. If you take for P and Q respectively -15 and -4, you get this equation, which we can rewrite slightly as this equation. People like to try out, by trial and error, simple values for such equations. And if you take for x the simple value 4 and insert this into the equation, you'll get 4 times 4 times 4 for x cubed, then -15 times 4, then -4. And if you calculate all these parts, you'll get 0. That is, 4 is a solution of this equation. However, if you insert the values for P and Q, that is respectively -15 and -4, into the formula, you'll get this. You may stop the video for a moment to check. And in the square roots, already trouble is looming. We get an expression with square root of -121. That's a weird expression, since square roots of negative numbers were not believed to exist. This expression actually was telling there is no value, no solution for your equation. On the other side, however, we have known by algebra that 4 is a value, a solution of our equation. People were baffled. They didn't know how to reconcile these two expressions, the simple 4 and the expression with the square roots of a negative number. Due to the rule, minus times minus is plus, see my other video on that, causing the square of even a negative number to become positive. An unshakable belief reigned that squares should be positive. And so square roots of negative numbers, like the one below, were dismissed as sophisms, that is, a reasoning with a hidden fallacy. Such square roots were thus squarely dismissed. They were called impossible or imaginary. The latter is not always the same as imagined. The case where the formula's square roots contained a negative number was named casus irreducibilis, irreducible case. Then people began trying. Bombelli was the first who laid aside his prejudices. Square root of -121. Couldn't one write the -121 as 121 times -1, underneath the square root, of course, and then split the square root according to the usual rules of algebra, which may, however, not apply in these cases? He just tried it. Then we get square root of 121 times square root of -1, and square root of 121 being 11. Could we write this as 11 times square root of -1, and thereby reduce the square root of every negative number to some number times the square root of -1? Bombelli used the above to calculate with an informed guess that solution that people knew to exist, 4. Later, others showed that the above, however, also contained a trap. After a century of experience and several successful uses of such impossible square roots, suspicion was still reigning, and the great Leibniz called roots of negative numbers sort of an amphibian between being and non-being. It took almost 300 years to free algebra of all contradictions, uncovering a highly elegant, powerful mathematics behind it, the mathematics of the so-called complex numbers. Complex numbers being numbers that consist of the conventional numbers that people knew of, like in our formula result below, the 2, and square roots of negative numbers, joined by a plus or a minus between them. The mathematicians' previous ideas on numbers had been primitive. That's what algebra was saying. And negative squares come from numbers that are, as it was then later discovered, neither positive nor negative. And in order to avoid confusion, some people substituted the square root of -1 by the letter I. Think of it as imaginary, but also as impossible, at least according to the former belief. After the rules for all of this had been sorted out, the famous mathematician Richard Dedekind pointed out that the rules for square roots of old-style numbers, still known by their relic name real numbers today, had actually never been proved in the strict sense of the word. Oh dear. He wrote this in Stetigkeit und irrationale Zahlen in 1872 under number 6 or paragraph 6. There is a translation of this book, Continuity and Irrational Numbers. Dedekind even published a book for his colleagues, Was sind und was sollen die Zahlen, in 1888. A rather informal title meaning, Numbers, what's that? It was translated less informally as The Nature and the Meaning of Numbers. In view of this mess, it's understandable that mathematicians felt the need to reorganize their teaching of numbers. There may have been even some embarrassment. Fact is, somehow a story spread teaching that all of a sudden mathematicians tore down their rule and demanded negative squares to solve a quadratic equation. Wait a minute. Quadratic? That is totally innocent to this very day. Well, the quadratic shifts the embarrassment to the bamboozled listener, though. Oh, and after that false story began to spread, it was discovered in 1926 that the laws of the atom follow the rules for imaginary numbers, respectively complex numbers. This is pointed out by Freeman Dyson in his article Birds and Frogs. Check the site of the American Mathematical Society. If all of this had been known by those mathematicians of the past, and their disciples who believed their masters had imagined square root of -1, perhaps one should have put in Haydn's manner a vigorous drum stroke here and there during the lecture. It means, of course, that one can rightly wonder whether the mathematical laws followed by the atoms are the first publication on complex numbers in the universe, though in a format that took us centuries to open and or read. Us.